Okay, hello. Cool. So, um, let's start in 3D. So
Mhm.
here's a 3D Rubik's Cube. I could let me turn down the animations. So I could show this way. This is a 3D Rubik's Cube, but we can uh, spread out the faces a bit and show back faces instead of front faces, and then also increase the FOV and space out the stickers a bit. Um, and I already have this preset. And now it looks something like this. And the reason we want to do this is if you're imagining you're like a 2D creature, now you can kind of see into it a lot more easily. So what we have here is there's six faces, but we only see five of them
Mhm.
because the sixth face would be covering up everything if we showed it. Um, when you do turns, if you do a full puzzle rotation, kind of like these two faces spin in place and everything else kind of rotates around. If you do a twist, seems to get the other color showing in. Notice that whatever side you twist, those stickers just spin in place. Um, whereas it's the like rim around them that move, that exchange places. 4D puzzle, basically the same idea, but instead of squares, we have cubes, and instead of six faces, we have eight faces, and the eighth one is pink, which I can display if I turn off Clip 4D, and also there we go. Bring that in. So we keep that hidden. And again, I can do twists, and you'll see that like if I twist the purple side, purple stays in place, and it's just the like rim around it on the other faces. So that's the basic gist of what this is and looks like and what's going on. Um,
Okay, so one thing I have
yeah.
yet to wrap my mind around is it looked like you just pressed like a non-center piece, and whereas like on the 3x3 you couldn't press
Yes.
a corner.
Yeah, that's an excellent question. So I actually can click on anything here, and it
Oh,
does the
okay,
same thing.
gotcha.
Because there's only one kind of rotation you can do in 2D. Basically, what we're doing here, when you twist a face of a 3D Rubik's Cube, you are selecting an orientation of a square. And there's only four, or a rotation of a square, I should say. There's only four rotations of a square. And one of them is identity. And the 180 you can get by just doing clockwise or counterclockwise twice. So if I right click, it goes clockwise. If I left click, it goes counterclockwise. That's like the standard we use in hypercubing.
Okay.
Um, but there's a lot more ways to twist a 4D shape. Oh, sorry. A lot more ways to twist a cube to rotate it. Um, and so
I
if I
see.
click basically, when I click on one of these, we call them ridge pieces, it rotates the cube around that ridge piece. Same thing with clicking an edge. It's rotating, like fixing that edge
Gotcha.
in
So
place
before we were
or
concerned
fixing the
with
corner.
the group operations on a 2D square, and now we're concerned with the two or the 3D group operations on a cube.
Yes, rotations of a cube.
Okay.
If you want reflections, we actually have that too. We don't have it in 4D. We do have it in 3D. So this is a puzzle that has mirror operations for a Rubik's Cube. And
Ooh.
we can even have mirror and twist. Um, so I can twist clockwise. I can also do like mirroring operations. And
Ooh.
this is a fantastic puzzle. Um, I highly recommend solving this puzzle.
I would love to try
Um,
that.
yeah, so Reflecube, non.ma/Reflecube. Um, this can be done in 4D. I don't think we've done this. Practice, do you know if MPU has 3 to the 4 by 1?
I don't.
Okay. There's
Um,
there's a program that might have this. We could build it as a five-dimensional puzzle. The same way that you could have a floppy cube. Um, this is
Right.
very, very close to a Refla square puzzle.
Right. That makes sense.
Yeah. And so we could do that one or two dimensions up. Um, so yeah, and
Elevate
then
a
you get
dimension
reflections.
to be able to do more
Yeah, to get
operations.
reflections.
That's
Exactly.
cool.
So and the reason for that is because a rotation is really a way of exchanging two axes, two dimensions. Um, and in the reason the 2D twisty puzzle doesn't really work is for a twisty puzzle, you need one dimension to stay fixed, one axis that is separating the pieces that twist from the ones that don't. And then the other two dimensions, you can do whatever transformation you want. And so the transformation in 3D, we can do rotations. And if you want to do reflections, you need an extra dimension that you just throw away to do your rotation through.
Right. That's the
Yeah.
the fake third dimension of the floppy cube.
Yes, exactly.
Okay,
So in the floppy cube, that's the white-yellow axis.
Yep.
Talking about this cube, not referring to the ones that let you do a 90-degree twist. Like this is assuming that you have to do a full 180. So not this. Actually, do I have that in here? I may be able to make it. Yes, I do have that puzzle. So this has only the 180 turns.
Cool.
Oh, the colors aren't great. Has the 90s, but you can't do them. Yeah. So yeah, and this is the old version, Hyperspeed Cube 1, which has been around for a few years. I'm working on Hyperspeed Cube 2, and this is a pre-release version of it.
So Hyperspeed
supports,
Cube is a program
yes.
that you made.
Yes, so I made Hyperspeed Cube.
Cool.
And this version of the program only does 3D. You can have any number of layers, and 4D, and it has to be cube or hypercube.
Gotcha.
Yeah. Why is it is possible. Why is it not? There we go. I can do more layers. So I'm working on a new version that has more shapes. So you may have seen before the Scube, which is vertex turning.
Yep.
Vertex turning cube. There's the FBO.
Sweet.
So these are different shapes in 3D, but we also have similar things in 4D.
Ooh.
So here's the shallow cut 24 cell.
Holy crap, that's beautiful.
Which is, yeah, which is sort of like a high dimensional FTO. Although I haven't solved this, so I don't know if it feels like that, but it looks like one. We have also the half cut version, which is much worse.
Okay, like effectively a 2x2
Yeah.
FTO.
Yes,
You say
it's
worse?
2x2 in the sense that it's because you're turning more of the puzzle at once. I haven't solved either of these, but I can almost guarantee you this puzzle is harder to solve. For the same reason that
a half cut FTO is
I
just a
search.
Scube, right? With the exception of like
Um,
center orientations existing and
yes.
orientations not existing, right? Like, isn't that
I-
strictly a sub puzzle of
yes.
the FTO? Like,
Sub puzzle of the FTO.
as in,
Don't.
you just remove pieces of the FTO.
I think so. Yes. But a Scube is only easy because it is very small. Generally speaking, half cut puzzles are actually pretty scary.
I'm reminded of
So
the half
Yeah.
cut, the half cut dodecahedron, like face turning dodecahedron.
yes, Pentultimate. I was
Yeah,
just about to
that
use
one.
that as an example.
Yes.
This is much scarier than almost any of the other dodecahedra. If I open, like, Curvy Star Minx is still pretty deep. But Star Minx, I haven't solved this, but I would rather solve a Star Minx than Pentultimate.
I think I've solved the right one and not the left one.
Yeah.
the left one's still on my list, my to-do list.
And even this is pretty deep, right?
Yeah.
You see, we're almost at the center. Whereas the Mega Minx, chill.
Yep.
And there's also the Mega Minx Crystal Intermediate, which I think has all the pieces of a Mega Minx and a... Pyraminx Crystal, this is one. Yeah, Pyraminx Crystal is not too bad, because it's so easy to isolate these pieces.
Right.
Yeah. So this supports different shapes. And the way that it does, these shapes are actually specified using a custom programming language. So this version of the program that I have here, they're specified using Lua, because I haven't ported most of the puzzle definitions.
The puzzle is specified in Lua.
Yes.
But
now I'm using... the program is written in Rust.
Okay.
But I can show you the HactarCE script, which is the custom programming language. This is a generator for an n to the 3 puzzle, like for any n, basically the 3x3, 4x4 in 3D, in HactarCE script. Most of this is just metadata, actually.
Wait. Hold on. Sorry. I'm
Yeah.
orienting myself.
Yeah,
here.
there's a lot going on.
What the heck am I looking at? Add.
So you're
buffer
looking at
generator.
the
So
yes.
you're defining the FT cube, which is the
yes face turning cube. Yeah.
So like this is a 4D hypercube, or a 3D hypercube.
This is 3.
Oh, so
3.
just a 3x3.
Yes.
Okay.
3x3 or 4x4, 5x5, etc.
Oh, it's the generator. So this is you.
Yeah, this is a
class
generator.
of
Yeah,
puzzles.
let's hold on. Let's start with a single puzzle. It's going to be easier. So I think let me just make sure. Oh, is it? No, okay. Let me just see if this is. Yeah, this is going to be easier.
Cool.
So let's start with a single puzzle because that's going to be much easier to explain. So this is the Diane Gem 3, which is a truncated octahedron. These are the triangle faces that got truncated. Here's the vertex that got truncated.
Yep.
So Diane Gem 3, we defined some ID, name. This is using Euclidean 3D space because I intend to have other geometries here in the future.
Ooh. Okay.
Yeah. Hyperbolic geometry is coming at some point. There's also 2D intersecting circle puzzles that someone's already working on that. Colors is VT octahedron. So down here we define a color system that defines all the default colors for this puzzle.
Okay.
And if I go here, here's a lot of them are unnamed. I need to clean that up. And some of them don't have default colors yet. But yeah. So this way you can reuse colors across puzzles. So vertex turning octahedron colors. So we define an octahedron, which this octahedron is defined in shapes. BC because it has BC3 symmetry. That's the Coxeter group. Okay, so here's the octahedron file, which a whole lot of metadata, and XOO is the notation. So this is getting real deep into the weeds. Basically, we can get the symmetry of an octahedron, which is also the symmetry of a cube, and optionally transform it, but we're not doing that. And this is a notation. Is this something you've seen before, Two-Spot?
Nope.
Okay, excellent. Are you familiar with the polytope Coxeter group constructions with mirrors?
I've heard the name, and that's all. I took a crystallography class a long time ago, but that's.
That's so cool.
I
okay.
do not really remember.
So you can construct regular polytopes in a really, really nice, elegant way using mirrors. And the Coxeter group, or Schlafly symbol, tells you the Schlafly symbol you can use to derive where those mirrors should be. In general, it's a Coxeter group. So actually, let me open Krita and start drawing these. And get some diagrams. Let's see. This works. Let's dark mode, because we've been in dark mode. Okay. So if we have a... basically, we can make a diagram with a bunch of nodes.
Mm-hmm.
And what we want to do is each of these nodes corresponds to a mirror plane. So this diagram, for example, or this set of mirror planes generates a cube. And the way that works is you start with any
vertex, and you can
any vertex. Yep. Yeah, exactly. So like this one, if you reflect it across green or blue, it doesn't go anywhere. But if you reflect it across red, it goes here.
Yep.
Then you can reflect it across green, across red, blue, red. You can keep reflecting points around, and eventually you'll generate all the vertices.
Mm-hmm.
And it's not just vertices. This works for edges as well. Anything, if you see this tiny little region that in here, there's a little little simplex here. This is the fundamental region of the cube. There's 48 copies of that region
Right.
that
Okay.
are the whole cube.
Yep.
And so what we can do is just define our cuts in terms of like one place along this region. So if we just say, well, put, a face right here, face right here at the, take the normal vector from the origin toward the plane. So if you take like the point on the plane that is closest to the origin, that gives you a vector that is perpendicular to the plane as well. And it tells you where it is and where it's pointing. That vector is in the red plane and in the green plane, but not in the blue plane. In fact,
Okay.
it's 1 unit away from the blue plane. And so that's what the letters XOO means. So let me make sure I get this right. Right, so for a cube, it should be OX. We are on the red, on the green, so distance 0 from those, which is O, and X means we're 1 unit away from the blue plane.
Are you suggesting that there's
Whereas
always precisely 3 such planes, such mirror planes?
no, there's more in higher dimensions.
Okay.
So the number of mirror planes is generally your number of dimensions.
Okay.
Yeah. So if I look at hypercube, that's OOOX.
Okay.
And so we're on the 4th plane.
What is we? You say
Octahedron.
we are on the 4th plane? That's
We need
you're
the
talking about the
point
vector
on
that points to the
vector
center.
specifying that facet rather.
What's a facet?
So in 3D, that's a face. So facet is a general
Generalization
term
of the
for
face.
the
Okay.
like n-1 dimensional element. So if you have an n-dimensional polytope, it's bounded by n-1 dimensional facets.
Okay.
So in 3D, those are faces. In 2D, those are edges. In 4D, those are cells.
Okay.
Yeah. So we can basically specify where our facet is using this notation of like.
So if you wanted
however many
an
letters.
edge-turning cube, you would say make the facet pole like OXO or XOO or something like that. I'm not sure which one it is in my head, but
so well the facet pole for this defines the shape here, but then or over here, we're defining the shape here with carve, and then later we'll add twists and add axes. And so the axes would be using you can use a vertex for that.
You're defining the geometry of the actual shape of the puzzle.
So we're defining the geometry of the shape and the puzzle itself. So in fact, we could make a cube right now. Hold on. Yes, let's try making this cube. And that might. I'm gonna add puzzle ID equals cube. Cube lid, and dim is 3. And build will be a function. So the first thing we need to do is, and I'm not going to say colors equals. No colors for now. Okay. So first, let's generate cubic symmetry, which is BC3. It's BC3, so we have cubic symmetry, and then I can say with cubic symmetry as our symmetry, and this is like a magic variable, basically. Carve cubic symmetry or sim.
And you
dot.
You said BC3 is the name of the Coxeter
group? Yes. So Coxeter groups here. Where's the list of them? Here they are. So, I was going to explain these diagrams, right? So there's a whole bunch of these symmetry groups generated by these reflecting planes. And they all of the spherical ones, the ones that generate polytopes, have names. And these are the names. And so this diagram I can explain. Each of these circles, each of these nodes, is one of our mirrors. Then the edge between them says what the angle is. So for a cube, for example, red and green. So let's actually label these. We'll have the red one, and the green one, and the blue one. So the angle between red and green is 45 degrees. That's pi on 4. Pi on 4. Yep. And green and blue. If we look at this, you'll see it's pi on 3.
Okay.
Because you can look at the hexagon there.
Yes.
Pi on 3. And angle between red and blue, if we look from here, you can see it's 90 degrees, pi on 2. Now, these are all pi over some integer.
Okay.
So for conciseness, when we write a Coxeter diagram, we don't write the pi divided by. You just write the number, the denominator.
Okay.
And the other thing is that by default, we use 2. Because if they're 90 degrees off, they're not really interacting very much. So we don't draw the edges that have 2s.
Okay.
And at all. Oh, whoops. And the other thing is, if we don't bother writing the 3s, because 3s are also common.
Okay.
And so you only write a number on the edge if it's not 3, and you don't even bother drawing the edges for 2s.
Okay.
And so now you can read these diagrams.
Okay,
I don't know why
okay,
there's a missing
I
dot
see.
right
So the
here.
dashes here are
Yeah, the dashes are for high dimensions. So AN is diagrams of this shape with any number of those. So this corresponds to simplices, right? There's a simplex in every dimension, which is like triangle, tetrahedron. The 4 simplex is like the equivalent in 4D. Oh, I started the Discord event. I didn't realize I have to start that.
Oops, yeah.
Okay. Yes. So, and then BN and CN, they're 2 different names. There's some historical reason for that, I'm sure.
So wait, just
there's
to
not
make
to be
sure I'm reading this
yeah.
right here for A sub n.
Yeah.
So like each of the
Mhm.
edges there. So like taking the 3-dimensional case, there would be 3 edges
Yeah.
here. Oh no, sorry, there would be
Yes.
2 edges.
No, two edges.
There'd be
2 edges, because
in-
there's only 3 nodes.
Right, and 2 of them have 3s, and one of them has a 2. Like
Correct.
there's an implicit
And
2.
yeah, I think they might show that. I don't think they show that here, but yes, yeah.
So like for E6,
and that will generate a tetrahedron.
Yeah, so for E6, there's implicitly like a click here, and like there's a whole bunch of the edges in that click are all 2s.
Yeah, almost all the edges in these diagrams are 2s. Okay, we got to catch axiomatic system up to speed as well. Yeah, I'm sorry.
Go for it.
Okay, so okay, real quick. Here's a 3D Rubik's cube. Here's what it looks like. Notice that when you do a turn, when you rotate a square, there's only like 2 options for what moves you want to do, because there's 4 rotations of a square, and that's really what we're doing when on a Rubik's cube. You're taking a chunk off, rotating it in any way you rotate a square, and putting it back on. 4D, we replace each of these squares with a cube, and we can take any rotation of a cube. And when I click here, I'm like taking the vector from where I click to the center, or really from the sticker that I click on to the center of the cell, and rotating around that vector. And just like in the 3D where we were hiding one face because it would cover everything up, here we're hiding the pink face because it would cover everything up if it were visible. So this is Hyperspeed Cube version 1, which I wrote. And I've been working on Hyperspeed Cube version 2, which supports other shapes as well, in 3D and in 4D. So we can pull in a 3 to the 4. This is the puzzle I just showed. But it also has much cooler puzzles, like the 24 cell, shallow cut 24 cell. So yeah, so we were just going through how the puzzle definitions for this work, which requires understanding Coxeter groups. So the basic idea here is that you can construct a polytope, like a cube, using mirrors. So you need 3 mirrors to construct a cube. And these mirrors basically tell you, they bound the fundamental region, which is simplex right here, this triangle, down to the core. And if you copy that 48 times by reflecting across the mirrors repeatedly, you can generate the whole cube. That's been a suggestion. Yes. Oh, interesting. The Bn equals Cn thing isn't just historical, it's related to deep connections to Dynkin diagrams and Lie algebras. Okay, cool. Do you have a? I'm curious to read more about that. If you have a link.
Wikipedia for Coxeter group.
Oh, it
will
says.
mention it.
Okay.
And then click on the link for Dynkin diagrams.
Okay. Thank you. Oh, because they're slightly different here. Interesting.
What is that? What is the double bond with an arrow? Directed double bond. That's
I
what I'm
don't
gonna call
know.
that.
They can be oriented?
Well, they can't for Coxeter groups. That's the thing. So
Right. Okay. Interesting. Specifically the threes. Or I guess the things that would be things that are not two. Okay, I'll have to read more about that another time. So we can, if each of these mirrors is one of the dots in this diagram, then this diagram tells you the angles between the mirrors. So if there's no line between two dots, then they have an angle of 90 degrees, pi over 2. And if there is a line with no label, it's pi on 3. And if there's a label, it's pi on that number. So this is pi over 4, pi over 5 is between those two. And they all have names. So AN, these are the symmetries of simplices. So if you just have two dots with a line between them, that's the symmetry of a triangle. 3 dots in a row is a tetrahedron. 4 is a 4 simplex, etc. This one, BNCN, these are for cube and octahedron, or hypercube, and generally the dual of the hypercube, whatever that is. Rhombic dodecahedron also is BNCN, because that's the edges of a cube, correspond to the faces of a rhombic dodecahedron. I think H3 is a dodecahedron, H4 is 120 cell. And this, I think F4 is the 24 cell. Sorry about the calendar notification. I think this is 24 cell. So there's friends that you'll recognize here. Okay. So if we're writing a puzzle definition for a cube, we want to carve with ooks. So this means OOX means the first, and BC3 canonically is the 02, 03, or sorry, 3, 4. Is that right? 4, 3, sorry. So canonically, this is defining 3 mirrors where the 4 is on the left. That's just what we decided as the convention for this program. So this is equivalent to saying CD43, which is this diagram where this is our first mirror, this is our second, this is our third. So OOX, the O means your distance 0 from that mirror. So distance 0, and distance 1 for the X. So this, if I print this out, print in.oox, I'm actually going to print out OOX, OXO, and XOO. So we can see what those vectors are. And I have to get the right version of the program. Should be this one. Refresh and try cube. And we get an error. Why? Because, right. We start from Euclid. This takes a list, maybe. Field does not exist. Because there we go. There we go. So here are the vectors. So this is our face vector. I don't know if you can see that.
Yeah.
Here's our face vector. Here's an edge vector for a cube. And here's a vertex vector.
Okay.
Now, those are not necessarily like actually the locations of those things. They're just pointing in the right direction. You still have to scale them.
Okay.
Now, the cool thing about this is if I change this to 5, 3, now we get face, edge, and vertex for dodecahedron.
Cool. That's awesome.
And yeah, so you can write quite generic puzzle definitions. The definition for a cube and a dodecahedron are basically the same in terms of how they're constructed. Or sorry, Rubik's Cube and Megaminx are basically the same in the construction. It's just
One of the
different metadata.
Yeah.
Yeah. These puzzle definitions are nice because the actual geometry of the puzzle ends up really, really easy to write, and you spend all your time worrying about the metadata, making the colors look nice and the names and everything.
Right.
So for cube, we want OOX. And if I do that, this is a vector. We want the plane. And this plane is the plane perpendicular to that vector that passes through that point.
You're carving.
Or
what does carve mean?
yes. So carve means cut with that plane and throw away everything on the other side of it.
Cut in the sense of geometrically cut the space, not
Yep.
like a twist cut.
Yes.
Okay.
Correct. Just cut. So I can demonstrate this if I carve plane sim.xoo, but I do that outside of the symmetry block. So this with sim means do this for every element of the symmetry. Now, in practice, what that does is that when you do this carve thing, it copies the plane around and then carves all of them. So this is what carve is doing, right? I just carved with the vertex plane.
Okay.
And I can normalize that vector and it'll cut much deeper. Dot unit there. There. So that's a much deeper cut.
That's awesome. This is cool.
In fact, let's thank you. Let's normalize the cube so that that's reasonable. Now I want names here. So if I go FD if I go to the cube here, let's snag this, and then I will explain what it is. I'm also going to rename this to just sim for short. So I think let's do face pole. We call them a plane pole is the vector pointing towards it. Pole. So I'm going to write this and then make sure it works and then explain what I just did. And then yes, so now we get nice cube colors.
Cool.
So what happens here, this is defining a map. So this array is a list of mirrors you jump through. The mirrors are labeled 0, 1, and 2. So the one we start at is F for front. And if you take F and jump through mirror number 2, you end up with U. And that's what we see in this demo here. If you start at F and you jump through the blue mirror, which is 2, because it's 0 indexed.
How are we defining
you end up
F
on
is?
top. F is just a name.
But like, how does it know that F
It's just a
is
name.
like a face? Like
F. So
faces
this is
opposed to
well, we're
line.
carving, so we're making faces, and
Okay.
I'm just saying F and saying this is what you should name that face. These are all strings, basically.
Okay. Yeah.
This is a map to key to value, and this colors is defined elsewhere. That's also defined in cube. Add color system. Here we go. This is what says that F should be green, R should be red, etc.
Mm-hmm.
For Western color scheme. Japanese color scheme, which we can also use, is slightly different.
Mm. Huh.
Yeah. The Japanese has a different color scheme. I don't know if new cubes in Japan actually use that color scheme, but historically it exists. So if you take F and you jump through mirror 2, you get to U. If you take U and you jump through mirror 1, you get to R, etc.
Okay.
And I could replace this by like inlining the sequence, and it would behave the same.
Right.
So basically multiplying mirrors.
Yep.
Here it's like a linear sequence, but it isn't always. Let's see this one. Yeah, so that's equivalent. So that's how we can name and color things.
Okay.
Let me just say
stop you real fast because I have a lot of questions.
Shapes BC cube. New dot pattern things. And I think that's the same. Yes, it is. Okay.
So
sim. Yeah.
You're defining.
Yeah.
Sim says like you have a list here But like these Coxeter diagrams are. Was it Dinkin
Yeah.
diagram? What I don't remember the name of the.
Yeah, Coxeter diagrams. Yes, not all of them are linear.
Yeah. So.
But
is there some
yeah,
magic going
no
on?
one's made
here?
an E6 puzzle yet, so we're not really
Okay.
worried about that.
Okay, gotcha.
And if you want, you can name E6. Most of the time, when we care, the ones we care about are going to be linear, and so
Okay.
this list notation only supports that.
And how does it implicitly know to add the two?
It's just everything else has twos between them. So if I specify a list, it's treating it like a line, where I'm just specifying the numbers for the edges
Okay.
here. In practice, you usually want to actually name the Coxeter group, which lets you get the E groups as well.
Gotcha.
But I just mentioned that to just say that like BC3 could be 4-3 or it could be 3-4, and we had to pick a convention. So we went with 4-3.
Okay.
Which means if I want an octahedron, I just make this XOO. And now here's an octahedron with incorrect colors.
That makes sense.
And I could also make it a rhombic dodecahedron. There we go.
Ooh.
So let's do a cube for now. So let's say I want those rhombic dodecahedron cuts. Actually, that's kind of fun. So I can, with the symmetry, add an axis at, or actually, let's slice the puzzle to show how that works. So if I do this, look at that. So what we just did is added cuts on all the edges. So if I take this and explode it a little bit, you'll be able to see a little more clearly. So you see we have that core is all connected, and then there's these edge cuts here. Now it doesn't actually turn, because we need to add an axis there. So that's our vector. And now, we have the axis, but it doesn't actually have any layers yet. So let's slice it at 1, at a distance of 1. And we have to say, where's that? So there's one cut here. Now what region should turn? Well, we want from infinity to 1. Oops. And now we can turn that.
Whoa.
So this is saying along this axis pointing toward the edge.
Yep.
Take a distance infinity to distance 1. That's our turning region. Now it doesn't actually have any. You see, as soon as I do anything, it snaps back because there's no twists defined.
Yeah.
We know that we can. This is the region we can turn, but we don't know how we can turn it.
Okay.
For that, we need to add a twist, and also we can get rid of slice because when you add an axis, it automatically slices.
Okay.
There's a way to turn that off. I don't remember exactly what it is. Yeah. So, and we can also say gizmo pole distance. Is that? No, when we add a twist, I think. Yep. Yeah. So let's add a twist on this axis. And the rotation that we want is spin dot through. What's the syntax on this? Right. Okay. So we want to go through mirrors 0 and 2. So if we look here at the diagram again, let's say that our twisting plane here is on the red and blue mirrors. So if you were sitting on these red and blue mirrors and you wanted to do a twist, you would take whatever your region is, reflect it through red, and then reflect through blue to get the 180-degree rotation. Yeah, because every rotation can be made by reflecting through an even number of mirrors. So this is our way of saying reflect through 2 and then reflect through 0. And that might go in the wrong direction. We'll see. And I'm going to put gizmo pole distance equals 1. And that's gonna. Did that work? Yes. So now we have twists.
What is gizmo pole distance?
Yes, I will explain in just a second. So I actually got this backwards.
Sorry, what was wrong?
Depending on the order.
What was wrong about the ordering?
So what's wrong is if these were
wrong?
not at a 90-degree angle,
Yeah.
then the angle between them, like if I specify the mirrors in the other order, it rotates the other direction.
So this is just saying
and
clockwise
so-
or counterclockwise turns.
Yeah, exactly. Clockwise or counterclockwise. And by convention, when I left click, it should go
Oh, I see.
It should go counterclockwise. And I'm left clicking now, but it's going the wrong way.
I see. I see.
So I refresh this. It's good. Yeah. So now I left click and it goes counterclockwise. I can slow down the animations a little bit. Yeah.
Cool.
So gizmo pole distance, you'll notice that this is easier to see on the 3 to the 4. Whenever I hover over something, there's this like bluish ghost thing. This we call the gizmo, which lets
Okay.
you do turns. So
see.
previously in Hyperspeed Cube 1, it was you click on a sticker to do a turn,
Gotcha.
which is great for a cube, for a hypercube, because each of these stickers corresponds nicely to a rotation.
There are symmetries though that don't
sometimes-
necessarily correspond to.
Yeah,
any
there's a lot of puzzles where that doesn't
cell.
work.
Okay.
And the other problem with this is it's confusing for beginners because it's not obvious to correspond stickers to turns.
Right.
What you actually want is to correspond ridges to turns. So if I pick this orange cell that I'm going to turn, and then pick an adjacent cell, a ridge is the boundary between cells, or boundary between facets, really. It's like the next element down. So really, I want to select, there shouldn't be a correspondence between turns and stickers. They should be separate separate objects. And that works nicely here. So that's what the gizmo is for. And in 3D, we have gizmos too, but you have to specify how far away the gizmo should be. Like here, the gizmo is at the cut plane.
Mm-hmm.
But we could make the gizmo bigger by making it twice as far away.
Okay.
And now the gizmo is very large.
That makes sense.
And this gizmo is its own polytope. You'll see it's a rhombic dodecahedron because that is our
Yeah.
axis system.
Yes.
Yes. And we could even have a hybrid axis system. If I wanted to have, because you'll see we do have cube turns, like there sort of looks like there's cube cuts. We could add those if we want. That's at distance, well, if this is distance 1 diagonally, then that intersects the plane. I don't know where it intersects the plane. How far away is this point? Greek geometry. Let's take a guess. I bet it's 1 over square root 2. That's my guess.
I'll guess 1 over square root 3. Not that I have any reason. Also, just a guess.
Okay. Let's see. Nope. That looks like halfway. So
It does. 1 over. Like 1 minus 1 over square root of 2 times 2 or something like that.
yeah. 1 minus. So we do 1 minus this
Yeah.
times 2. I bet that'll do it.
Yeah.
There
That's
we
right.
go. Yeah. There's probably a nicer expression. So now we have that axis and we have that turn as well. Because I added sim through 1, 0 for that. And we have this.
Cool.
So if you have multiple different kinds of turns, then you'll want to adjust the gizmo distances to be nice.
Right. That makes sense.
Yeah. Let's use gizmo distance 1. That's pretty nice for this.
Yeah, that's pretty. Okay.
So yeah, we just made a puzzle.
Sweet.
Yeah.
Yeah, that makes sense.
So this is how you make puzzles, and we can do this in 4D as well. In fact, if I can make this puzzle 4-dimensional quite easily. If I just run through here and change everything that looks 3D to something that looks 4D.
Mm-hmm.
Let's see. 2, 0. This is going to be a problem, but we'll get there. Oh. Okay. And then if I run this again, boom, we have a 4D puzzle.
Ooh, that's sick.
Yeah. And it even has these turns.
Whoa.
There's some bugs. So what's happening here? What is happening here? This should be, the problem is that 2, we have it landing on 2. So this should be XO, probably, if we want to use mirrors 2 and 0. So because if you're trying to do a transformation, remember I said earlier that, actually this is better done in here. So every rotation, you pick some axis along which to cut, and the perpendicular space is where you do your rotations. But if your rotation includes the axis along which you cut, then that's like not good
Yeah.
geometrically,
Yeah.
and that causes problems. And I don't detect that right now. I probably should. So this should fix it. Rebuilding the puzzle, and there we go. Yeah, this looks much more well behaved. Also, much more, a lot more cuts.
There are a lot of cuts there.
Yeah, this is a nasty looking puzzle, but it is a puzzle, and we just generated it. Probably this thing's probably square root 3 now
Oh.
because higher rank. Maybe not.
That looks even worse.
Yeah. I don't know. Anyway, yeah, we can make those. Now,
Cool. Yeah.
something funny is happening. These gizmos, there's nothing bounding. This is an infinite hexagonal prism.
Uh-huh.
That is this gizmo.
Okay.
There's nothing bounding it on top here, and that's in this case that indicates a missing turn. Like there is actually a turn you could do there, right? You could imagine
Oh.
if I do this,
Right.
I just did a 3 cycle of
Uh-huh.
those guys, which is a rotation that would correspond to the top of this hexagonal prism.
Right.
So for a polished puzzle, we should really add that twist, and that would cap off the prism.
Okay.
But also, I need to add a way to bound these prisms and stuff anyway, because sometimes you want to do that. And so you'll notice this is very little code that we just used to define a complicated puzzle with like a
Yes.
hybrid axis system, which I'm quite happy with. I should probably learn these different things.
That
like
is
X1,
indeed
X2.
awesome.
Yeah. And we can even do things with different symmetries. So let's go back to 3D. Let's call this, let's keep it skewed. That's small, but it's fine. Let's say that I
I've ever
have.
seen that thing.
Yeah. Yes. So we can do something fun here. With BC3, we'll define a face hole and we'll carve. And then if sim equals H3, H3 is dodecahedral symmetry. We'll say classic hole is sim dot h dot unit typically hash sim. So I'm going to write a bit of code here, and then affinity to 1 is fine for now. It should be 1, 0. Okay. So I refresh Xmap because. Okay, so here is a hexaminx,
Whoa.
I think. This is a megaminx, effectively in the shape of a cube. Now this one is a little bit nasty. You'll see we have some floating pieces. But if we make the cuts a little bit deeper, that should go away. Here. Better. That might be too deep.
Oh, is it no longer?
This might actually.
Mechanically a hexaminx?
This is not quite a hexaminx. So the problem
It's like
here
a
is that we haven't
star
lined
minx
up the
that's
symmetries.
been-
Yeah.
Something like that.
This is a dodecahedron shape modded into a cube,
Right.
or a megaminx shape modded into a cube. So it's
Yeah.
but it's not a hexaminx because
The cuts are not...
hexaminx you have to line up the
Right,
symmetries
yeah.
nicely.
Yeah.
Yeah, which I think is possible, but I don't know exactly the transformation to do it. But we could take this symmetry and transform it. We could take the cubic symmetry and transform it correctly to line up with the dodecahedron.
Right.
Probably it's a little nicer if we do it the other way. Missing coset. Right. Did I not? Oh, it's H. Right. Here we go. Here's a. Oh dear. How did this happen?
So this is a cube shape modded into a dodecahedron that we're looking at now?
Yes, and some of the pieces disappeared.
Well, I think they're outside of the cuts, right?
No, it just removed them because it thought they were internal pieces.
Oh.
Okay, we need this to be deeper cut.
Oh, it identifies internal pieces.
Yeah, so yeah, it removes internal pieces.
Huh.
unless I disable that behavior. So here we have this internal
Oh,
cube.
wow.
But if I set remove internals defaults to true, then
What
now
would
it moved that
happen
internal
if
cube.
you had internal pieces on a 3x3x3x3?
Fantastic question. They are not rendered. So what it would look like is absolute chaos. Um, yeah, so here you'll see that we can see these like internal faces of the stickers, of the pieces, even though we don't have internal pieces. But if I uncheck this, we don't have those. This is what we do in 4D.
Okay. Wait, I'm doubting the sanity of my own question now, because in a 3x3 there is no, like on a 3x3x3
Mhm.
there is no
Yeah.
like there's no internal piece other than the core itself, and that's different on a
Right.
3x3x3x3.
So on 3 to the 3, there's a core, which we are not showing. In fact, it's removed from this puzzle,
right.
but it existed there once.
Yes.
Um,
Okay. Yeah.
That would be true on a 3 to the 4. There would be a single internal piece, but all of the external pieces also have internal faces, or sorry, internal facets, internal cells. Is that? Yes. So, for example, this is one piece
Yeah.
with 4 stickers. Those stickers are the cells of that piece, because that piece is a 4-dimensional solid. It has 4 more cells that would be gray because there's no stickers on them.
It has 4 more stickers
Yes.
that would be gray. Yeah, because they point
4
in
more
no
cells.
direction. Yes.
4 more cells that are like on the inside of the puzzle.
Yeah.
Right. One of those cells is separating this piece from this piece.
Yes.
Another one is separating these 2 pieces.
Yes.
Another one is separating these 2 pieces.
Right.
And yeah.
Where's the 4th one?
Let's see. One is to there, 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 and there. That's the 4 directions. Because there's 4 pieces that are adjacent to it.
To that thing. There's 4 pieces.
So that's one of them. That's one of them. That's one of them. And this is one of them.
Wait, did you not just show the same thing? Oh, that one's not on the purple cube.
Correct.
Oh, okay. Yeah.
Right, because there's another direction. So I could actually, this might be easier if I center that piece here. So now that piece is in the very center of our camera here.
Okay.
And it's maybe easier to see that there's 4 directions you can go.
Yes.
And each of those pieces has some cell there's like a cell boundary between them. So yeah, we don't show those because it would be chaos.
Gotcha.
I don't know if I can.
Wait, you're saying
Yeah.
the cell, the boundary between the 2 cells
Yeah,
is itself
so-
the...
The boundary between 2 stickers, or sorry, 2 pieces is a cell. So here's a piece.
Yeah.
Right, this is a 3-dimensional solid.
Yeah.
It has 6 bounding faces.
Yes.
One of its bounding faces, this gray one, is separating it from an adjacent piece.
Yes.
In 4D, this piece is a 4-dimensional solid.
Yes.
It has 8 bounding cells. 4 of them are stickers that we see.
Is a sticker effectively? Or a sticker
Stickers are cells.
Stickers are
So
cells, but
a cell
not
is
cells.
what a cell really is.
Uh-huh.
A cell is an element of a polytope that is that is like 3-dimensional.
Okay.
That's what a cell is.
Okay.
And so a hypercube, which this piece is a hypercube, a small
Okay.
hypercube.
Yes.
So when I say cell in the context of puzzles, this puzzle has 8 cells. But this piece also has its own 8 little cells. The same way that this puzzle has 6 faces. And this piece also has 6 faces.
Okay, yes.
3 of those faces are stickers.
Right.
3 of them, which I can even filter this if I get really fancy. 3 of them are internal.
Yeah. Okay. Yeah, that makes sense.
Okay.
But
Yeah.
and how does that show that there are
Yes.
supposed to be internal pieces?
So I'm just saying that there would be internal cells. If I show the same way that I showed gray here,
Mm-hmm.
if I showed that gray in this view, it
Right.
would be absolute chaos because all of these pieces would have those internal things.
Okay.
So before we even show the internal pieces, like even if I set keep internals to be, or remove internals equals false to keep the internal pieces, you wouldn't see them because I'm hiding those gray faces, or those gray cells.
Mhm.
And I don't remember what it looks like with those on. If you want, I could spend a couple minutes
That's
trying to
okay.
trying
That's
to
okay.
display
That's
them.
okay.
But yeah, I don't
I can
remember
imagine it would be
exactly.
chaos.
Yeah. Um, so yes. So that's yeah, so we have those gray ones here. So this is a cube, or a cube shape modded into a dodecahedron.
Mm-hmm.
We can do. This looks much nicer than the other way around. Yeah, so we can make shape mods pretty easily. We can do hybrid access systems.
Mm-hmm.
I can even, if I go into I haven't ported a lot of them, but if I go back to the Lua definitions, there are other funny things we can do. So this engine actually does support jumbling. Here's a Bagua cube. You'll see it.
Ooh.
I can't turn this because those pieces are blocking it.
Right.
But yeah, we can do jumbling turns just fine. Now this puzzle right now is not implemented correctly because I show the triangle pieces. These triangles should all be the same, but you'll see they actually have slightly different shapes. So this puzzle has bug. But that's the puzzle definition, just needs to be written better.
Mm-hmm.
So
Okay.
we can simulate some kind of crazy puzzles.
How
And
does
we
it-
can do
how
this
does
in
it-
4D.
It just
in theory.
identifies.
Yeah.
In general, it just identifies if there's ever like a, what's it called,
Blocking, yeah.
blocking. There isn't
Yeah,
a way that
so
you could
it's actually
make it-
not so hard.
Uh-huh.
Yeah. All you have to do is look at every single piece and check whether it is inside of the twisting region.
I see.
So there's this region of pieces that twist.
Right.
If a piece is inside, it has the twist applied. If it's
Right.
outside, it doesn't. And if it is partially inside and partially outside, then it's blocking the turn.
Gotcha. Okay.
Yeah.
Cool.
And we can do jumbling puzzles in higher dimensions. So here's a test we made of a puzzle a 4D puzzle
Holy
that
crap.
jumbles. Actually, let me get a better one. Let's see. FTRD Prism. This is better. So the face-turning rhombic dodecahedron is a famous 3D puzzle that has jumbling turns. And I can show you that jumbling here. Let's see. Maybe I can't.
Isn't that it right there?
Hold on.
That's happening.
Let me FTRD. Let me get the original face-turning. Do we not have a face-turning rhombic dodecahedron? Okay. Yes. So that. Oh, there it is. Yeah. So I can rotate this away. Oh, I don't have the 180 turns. That's the problem here. If I had 180 turns, I could. Or there we go. That works. Maybe. There we go. Yeah. So yes, this is what the 3D puzzle would look like. If you do some of the jumbling turns.
Right.
Yes. And so 4D jumbling, we don't yet know how to. We don't even have a theory for like how to work with these puzzles because they get really, really weird. So if I reset this puzzle,
When you say a theory, are you implying you have a theory for
yeah.
how to solve them in 3D?
not even solve. I mean like interact with them.
Oh.
Like this is simulating it, but not in a way that is like good. Because look at this. I can do this rotation, or sorry, I can do this rotation. And then now, because this is 4D, I could just rotate that around to here. And now I have this funny rotated bit on this face.
Mm-hmm.
I could rotate that away. And I could basically take these funny rotations anywhere else. And there's nothing stopping me from giving this another funny rotation, even more. You end up with funny rotations just permeating the whole system. In 3D, if I have, do I have a helicopter cube? Do I have a? Oh no, do I not have a 3D jumbling puzzle? that is. Oh, Bagua mix will do it. Maybe. Is it? No. This is 45 degrees. I want something that's spookier than 45 degrees. Is this? No. That should jumble, but it doesn't yet. Except Q plus. That's still only 45 degrees. In 3D, you end up with basically you can only mess up one face by like some arbitrary angle. Like let's take a Rubik's cube actually. So if I have a normal Rubik's cube, I can rotate this by some nasty angle.
Yeah.
But then I can't do anything with it, right?
Yeah.
I have to line it up with other faces, but in order to actually make turns.
Yes.
The spooky thing is that in 4D, I can just like I could take this face, turn it by whatever angle I want. That is maybe irrational, maybe doesn't line up with anything. But then I can take those pieces away.
Take them away, meaning?
So I can still make turns. And so now these pieces are at some nasty angle, and I actually can't really fix those pieces directly because we only allow,
So there's no insert. So hold on. So like, they don't start to misalign with things when you.
If I wanted to actually do anything, like I can move them around as a block, but if I want to separate these pieces, I basically have to take them back where they came from and undo whatever nasty angle I did.
Right. Wait, so can you demonstrate that on the 3x3, like on the 4D, on the 3 to the 4? Is that what you said?
Yes, actually.
So like, where's the single irrational turn that you're doing, and how do other things still work after it?
Yeah, so let me go here. I think the way to do this is to modify the hypercube definition to do 30-degree increments, or 45-degree increments will work. Let's see. Twist system.
You introduced that as a 4D phenomenon. Is that because the fact that you can have two independent rotation planes means you can basically like take the bad angle and completely remove it from your other rotations that you're doing, or is it?
It's
or is it
because we
deeper
have
than that?
turns that commute and overlap. So in 3D twisty puzzles, I think you never have turns that affect the same pieces or have overlap in what pieces they affect and commute with each other. It's very rare.
Is related to how the mechanical hypercube technically just jumbles, right?
Yeah. So yeah, I'm gonna demonstrate that. Mechanical hypercube is a whole thing. I think if I do this,
rotate it by any angle and take that angle anywhere else.
This is this
and
version.
It just doesn't care.
So if I refresh this, nope. Why is that not it? Because it twists. Oh, that's cubic axis system. That's my problem. I need the twist system.
So if there's
here.
two independent angles that can be like composed and in a way that commutes, then does that mean that you can do up to two arbitrary, like, strange angles before weird things start to happen? Is that what that implies, or am
I? Sorry, I'm not sure what you mean.
Like in the 3x3 case, we were able to do one move, and then we weren't able to do we were able to do one irrational angle turn and then not a second one. Does that mean in this case we're able to do two on two independent angles and then a third one will be blocked, or something like that?
Angles and then a third one will be blocked.
Or can you just continue
I don't think so.
Indefinitely composing like bizarre angle turns?
You can keep going basically. I'm gonna try to demonstrate this by commenting out a whole lot of things I don't care about. Why is it stuck building the puzzle? That's Not great. Let's see. Pretty sure I go X to Y. This is very strange. I'm gonna try restarting the program. Because it shouldn't take any longer to build. Okay. Aha. It's right. These types don't care.
Axiomatic system says the point of my question is whether the two independent rotations are able to mutually unblock one another somehow.
I don't. I'm not sure. I don't think that's the thing that's going on here. Hold on. This will. What's this? I'm sorry. Let's see.
All good.
Deface. Oh, we have end of the D generator. Oh, I could just use this then. That's gonna be easier. Three to the 4. And I gizmo voltages. Bingo! There we go. Okay.
Ooh.
Yes. So if I can do a 30-degree turn here,
Yeah.
then now I can take that 30-degree turn
Wait,
elsewhere.
wait, slow down, slow down, slow down. Do that again.
Yeah,
Hold
okay,
on.
sorry. So this is a hypercube,
Yeah.
where all of my turns are in increments of 30 degrees.
Yep. Just
Which
do that
is
one
fine.
turn one more time. The one, yeah, that.
Yeah, I can just take this around elsewhere.
Whoa,
Right, this is legit.
What? Wait. Go back. Just do and undo the first turn
Okay,
like
yeah.
50 times over.
Reset. Okay, so we do this.
Yeah.
Yep.
Uh-huh. Huh?
So,
What?
right. These are the pieces affected by that. If I do
Yeah.
this,
Yeah.
right, these guys are just rotating in a circle, same
Right.
distance from this face.
Right.
Right, if I take it here, oh, I don't like that, never mind. Yeah, right?
What the heck?
I'm rotating here.
Yeah.
I can do that. I can rotate this.
Right. What? So that's
Now,
not
right
just gonna
now, if I try to
shapeshift, that's
turn
also gonna jumble?
Well, this isn't. Well, jumbling is. I haven't actually defined jumbling yet, which is maybe a mistake.
Defined
But yes, this
programmatically or
jumps.
defined in words for this?
In mathematically.
Okay.
So a jumbling puzzle is one that cannot be unbandaged finitely. If you
Ooh.
try to break apart pieces to allow turns, to prevent turns from blocking, you'll have to break apart pieces infinitely many times.
Okay.
So and that's true of this puzzle. But there's actually an even worse problem than what I'm showing here. This right here is bad, but it's not the real problem. The real problem is that just the twists, just these rotations composed together, I'm just doing 30-degree rotations,
Right.
but I'm wandering off in state space.
Right.
I'm now completely blocked myself, and there's nothing I can do.
I see.
But we need those turns, because what if I do a 30-degree turn here? I need to be able to make an arbitrary 30-degree turn there, and then maybe, like, turn it off to here so that I can access it from here. Now I've blocked things, but, like, let's put that there. Over here, this guy can turn. And maybe we turn it back. So we're not sure how much control to give, where the turning stops should be.
Mm-hmm.
Because like on a curvicopter, this is a jumbling puzzle in 3D. You can make this angle here. This is an edge turning cube.
Yeah.
Right. You can turn the edge by some nasty jumbling angle that I don't remember. It's probably like I don't know what angle it is. And then make another turn and it jumbles. But there's a finite number, like this piece here has a finite number of orientations where you'll ever be able to make a move.
Yeah.
Because we could rotate, like I just made this out of a cube. You could rotate, or hypercube. You could rotate this by any number of degrees and still be able to make this turn.
Yep.
And so it's not clear where we should stop.
Right.
Um,
yeah. The puzzle
so-
geometry itself
yeah.
doesn't instruct you on where you could.
Right. Now, there's something interesting that's implied here. This region of 9 pieces actually can turn, like mechanically, if you were to build one of these in 4-dimensional space with rigid body physics in 4D, then these 9 pieces would be able to rotate in their own plane independently of the orange and pink faces here. As far as we know, there's no way to stop this. If you actually build one of these in 4D.
Right.
We don't simulate a puzzle that does that. So maybe the problem here is actually just that we're trying to impose constraints on this that don't make sense. But we're quite attached to the notion of a cell turning hypercube rather than turning 9 pieces at once, because that's a more boring puzzle. It's easier to solve. So that's one of the funny things going on with jumbling in 4D.
So does I want to go back to you said it's called jumbling the like where if you keep cutting things along axes where they like want to stop, then you get infinitely more pieces. Does that map onto the common like layman definition of jumbling?
The layman definition is that it's just people are wrong sometimes.
Okay. That's what I was wondering.
Sometimes people will say jumbling when what they mean is shapeshifting.
What's an example of that? Would the curvy copter be an example of that?
Curvy copter jumbles and shapeshifts.
It does jumble under your definition, you mean?
Yes, it does jumble. Yes, under this definition, because the rhombic dodecahedron, it's rhombic dodecahedral axis system is what it is.
Right.
And if you look at the angle that it does, the angle is irrational. So if you keep if you can try to unbandage a curvy copter, in which case you get curvy copter plus.
Right.
This is unbandaged. This allows slightly more turns than the curvy copter. But even the curvy copter plus, you can get to a place where you would like to be able to make a turn but can't because you're blocked. And if you try to unbandage it more, it just gets smaller and smaller pieces.
Where do they show up?
And you could. Yeah.
Sorry, you're saying that's there's irrational angles here? Is it not just 30 degrees and then there's two opposing orientations are illegal?
Let's open P-cubes because that will help.
What's P-cubes?
P-cubes is a 3D puzzle simulator that kind of does what HactarCE does, where you have a custom programming language and you can build puzzles. The thing is that the custom programming language is an undocumented variation of HactarCE and does not have good geometry primitives. But it has a lot of puzzles. So let's find curvy copter. It also only runs on Windows, so I'm running this through Wine. Curvy copter, here we go. So this is equivalent to a curvy copter.
Okay.
Just the cuts are straight because P-cubes can't do curved cuts.
Okay.
So here's where we get the blocked turn here. I want to turn the white-orange edge, but this piece here is blocking me.
Right, that's where the curvy copter plus shows up.
Yes, so the curvy copter plus, I do the same thing. I can make this turn. But now this turn is blocked. The blue-orange.
Wait, slow down. Hold on, where? The
blue-orange is blocked.
Okay.
So I want to turn
it's
this
blocked
edge
on the edge there?
on this piece, these two.
Oh, okay.
Actually, these 3, maybe 4.
Okay.
Explode a little bit and try to see.
So anytime you have your rational angles, you're always going to get jumbling.
I think that is basically true. You could have a cuboid. Is that true? I'm pretty sure that's true. Yeah.
Okay.
You might be able to do something, some contrived puzzle with irrational angles that technically does not ever block turns. In fact, you can, yeah, if you'd like, because you could also just have empty gaps. In which case, I don't know if it counts as jumbling.
Like non-existent like pieces that are just removed or something.
Yeah, you could, like that's what they did. Well, here it's gray, but you could imagine just having gaps in the mechanism,
Mm-hmm.
and at least in simulating the puzzle.
Okay.
Yeah, and I don't know how that's classified as. But yeah, irrational angles are usually a telltale sign of jumbling.
Okay. Yeah.
If we look at the Bagua cube, these are 45 degrees turns, which are not irrational angles. But if I do a 45-degree turn of the cube, and then, or 45-degree turn, and then a 45-degree turn along this axis,
and then another 45.
those add up to an irrational angle.
I see.
And that's where the jumbling comes from here.
I see.
Yeah. So, open question whether we can make 4D jumbling puzzles that are actually reasonable to interact with.
Gotcha.
It's one of the goals of this program is to give us a space to research that.
Cool.
Yeah. So I think that's all of the puzzle theory things that I know of. Oh, I can, as an aside, there's several different kinds of simplex. So in 3D you have the do I really not have the shallow tetrahedron? Anyway, in 3D you have a pyraminx. Let's see.
Yeah.
Pyraminx looks like this. Lots of people love this. It's weird. It kind of has 3 layers. It's not really the shallow cut tetrahedron. That would be the Jinx pyraminx or Halpermeyer tetrahedron, which looks like this. So this is the shallow cut tetrahedron.
Shallow from the perspective of the face, because I guess it's
Of the face, yes. Shallow cut face turning tetrahedron.
Okay.
Yeah. This is not shallow in any sense. You could do it as either vertex cut or face cut.
Mm-hmm.
Either way, you have to add an extra cut for the tips.
Yep.
So we have 4 simplices in 4D. We have the simplex A, which is like, or let's start with C. This is like the Jinx pyraminx, shallow cut.
Okay.
On the faces. Let's get do I only have access to vertex turns? Apparently I only have access to vertex turns. That's strange. So yeah, this one's shallow cut on the faces. We have, let's see, we have this one, which is slightly less shallow, and this one, which is less shallow still. So the cuts are gradually getting deeper. And we have Pura, which is a combination. So this is like the 4-dimensional pyraminx kind of.
Okay.
It has the trivial tips and these turns. So that's fun.
That is fun.
24 cell I already showed, the half cut. We could do shape-shifting puzzles in 4D though, without much difficulty. So this is a half-cut 48 cell shaped like a 24 cell. So we took a 48 cell, which has a bunch of, actually I don't know, we have a 48 cell here? No, I don't have a 48 cell to show just the shape, but here's a 48 cell, the axis system that's shaped like a hypercube. So this is doctrinaire, meaning it does not jumble, and all moves are always accessible. So which means I can scramble it.
Is that a
Doctrinaire? Yes. Doctrinaire is the term that means all moves are always accessible. There's no blocked moves ever.
Is that a cubing term as opposed to a math term, or?
I know it's a term in puzzle theory, the cubing stuff. Don't know. I don't think it's a math term, but I'm not sure. Oh yeah. No. Okay, this is not.
Oh.
Yeah. So that's a cubing term then. Yeah.
That is insane.
Yeah. I would like to solve this once we have everything set up because it looks so cool. Unfortunately, it's half cut, so actually maybe I don't want to solve this. That looks so cool. And we have the same puzzle with so many different cuts. So here's a 16 cell shaped version of it, which is just great. Yeah.
Cool.
Yeah.
Anything else you want to talk about?
Um,
Anyone have any questions also? I've been
Yeah,
talking
questions.
most of the time.
I have about 1,000 questions.
Please ask. Yeah.
First, this is very minor, but I'm just curious. The Lua logs in the corner often have complained about like identical twist most of the time, and I mean that was
Yeah.
at least early on. That was the most common thing.
Identical twist already exists with ID. Yes. Um, yeah, this is a mess.
Okay.
This is also the definition is written poorly. So the definition is probably written in such a way. So with one of the reasons I switched from Lua to custom programming language is these with symmetry blocks. This basically executes the code once, but each operation expands it, which is great because it means that like if I carve a face, it executes only 6 times on a cube. But if I carve on the edge of a cube, it'll execute 12 times. In Lua, I was using for loops, where it would just loop over every element of the symmetry. And that means that sometimes you would get, like, if you try to carve a cube by looping over every element of cubic symmetry, you're going to carve 48 times when you only needed to carve 6 times. And unless you're careful, the same thing happens when you're defining twists. And a lot of the puzzles, this is the older version that uses Lua, almost all of these puzzles were just written, oh, I should not have started the evil 120 cell. Almost all these puzzles were written when we were just like testing things to see what happened, because this is the first time we had an easy way to make these puzzles. And so they're really sloppy and like not written well. In the future, I want to polish them. This 24 cell is an example of one that was polished. Like you see, it has really nice colors because we sat down for 30 minutes and we're like, how do we color a 24 cell? So yeah, there's a lot of rough edges around this program that I'm working on cleaning up. One of the difficult things is we have to name the twists. So a program like P-Cubes basically depends on it depends on the order the puzzle generates, because every twist has an ID. So each of the twists I'm doing now has some sort of ID. And when you save a file that is like, here's a log file of my solve, when you save that file, it just saves a list of all the numbers of the twists you did. Problem is, I want to be able to optimize things in the future. If we find a better way to construct puzzles, I want to be able to change that. So the log file has to save, like with notation, the twists. And that means you have to name all the twists. And those names have to be stable. So that makes these puzzle definitions much more difficult. But also, we want to have notation for these puzzles too. So we should have that anyway. Let me reduce the outlines here.
So is the goal there to kind of come up with ways of like constructing labels for twists?
Yeah, we want to have good notation for things.
As opposed
Yes.
to just like
Yeah,
naming them.
those are
by
just
hand.
randomly.
Yeah.
Right. We want to basically have a specification so that if we make other programs that interoperate, or if we want to change the puzzle definition, or if I change the algorithm that generates the shapes, we can basically check to say, like, does this match the spec for how we do notation on this puzzle?
Gotcha.
That spec might not be formally written. It might just be like, here, look at this version of the program, we implemented it.
Yeah.
But it should at least be sane and reasonable.
Yep.
You should look at it and be like, oh, that makes sense.
Yep.
Yeah. This is the evil 120 cell, which is very, very deep cut. And to contrast with the shallow 120 cell, which is not evil at all. See, very non-evil.
Your definition of evil and mine might be very different.
This puzzle is not hard to solve. It just takes a very, very long time. It's evil in one way. This takes a very, very long time and is evil.
120 cell is the 4D version of a dodecahedron, is that correct?
Yeah, you could think of it that way.
Okay.
It's H3 as opposed to H2.
Okay.
is a symmetry group, and it's again like sitting on the this node here, I think.
Wait, H3 was. I thought H3 was the.
Sorry, H4 as opposed to H3.
Okay.
My bad.
Gotcha.
H4 as opposed to H3.
Okay.
Yeah.
So you just
Or-
slap another 3 in there.
Yeah, exactly.
Okay.
Which that 3 corresponds to 3 dodecahedra around one edge.
Okay.
So if I reset this puzzle and show just 2 of these faces, and put that in the middle, let's do that. Here we go. So here I've highlighted just the pieces that are part of one edge. You can shrink those together, space them apart. Let's not do that. Facet there. So you'll see that this edge, there's 3 dodecahedra around that one edge. That's the 3
Okay. Yeah.
as that last.
Yep.
Yeah. It's hard to see them. Actually, I can. Oh, I know what to do. This is gonna be very cool. If I go into styles and add a new style that is invisible with 0 opacity, and set most of these to invisible, and then not show that. Great. So we have that. Then I say this should be shown with hidden. Let's do RI or RU. Look at that. So
Oh,
now,
that is the 3 dodecahedra that are involved.
yeah, exactly. You can see them
Cool.
right here. Those are the 3 dodecahedra around one edge.
Cool.
Yeah, I really like this ability to like either use checkboxes or text and to show pieces with like multiple different styles.
Yeah.
See, is it not letting me do turns for some reason? That's weird. Oh no, it is. It's just the pieces I was trying to turn are all invisible. There we go. Now, you can even full scramble, and then this was it speeds up because it starts caching the.
That looks like it was not a good idea.
Yeah, it's not a terrible idea because it speeds up as it caches the transformations. What I want to do is optimize this to pre-compute the group operations, or the pre-compute the multiplication table for the group, basically, which will help massively. So that's where our 3 friends ended up.
Oh wow! So
Yeah.
is that?
Mhm.
I don't know anything about how you guys do this in practice, but like,
Yeah.
is this? Would it be legal in? I don't know if you have tournaments or what, but would it be?
Yeah. Oh
legal
yeah,
for-
we have leaderboards.
Oh cool.
So
is it legal to
we
highlight
have the
things
official
and then-
leaderboards.
and then like solve that face while it's highlighted? Because I can imagine that's incredibly
Yeah.
helpful. Like,
So I can actually do a speed solve live and show you what it's like. I can if the program
Yes,
will load. Hold on.
please.
So it needs keybinds, it doesn't need them, but it's much faster with keybinds. So here I'll have the keybinds reference open and make this go much faster, or else I will be annoyed. So you can see what keys I'm pressing. So the default keybinds, you basically hold one of these keys to select which cell you want to turn, and then press one of these 6 keys to do a twist. So
Ooh,
it's that's that, and that's
Okay.
that way.
right.
And I've added more keybinds for myself because I want 180s
Yeah.
as well. And I can also hold X to do full puzzle rotation, or hold one of these and hit space to recenter. So if I select, let's say I select yellow and hit space, now yellow's in the middle. Select blue, hit space, it's in the middle. But these keybinds are customizable, and you can even make separate groups. So I have an RKT mode, which is a solving technique where these correspond to 3D keybinds. So that's useful. And I have another mode called 2gen, which is not quite 2 generators, but it's where I have access to all of the I moves here and all the R moves here, I being the inside. So, and this is useful for most of the solve. I just need these 2 faces and
Right.
L moves as well. And that way, because in the default keybinds, I have to press 2 keys to do anything.
Uh-huh.
But in this mode, it's 1 key.
So that
There
would
are
be
people
like
who are
ZZ,
competitive.
4D ZZ
Yeah.
or something.
Yeah. So there are people who are competitive with the default keybinds, but both of the top two slots in the leaderboard, and possibly more. I'm number 2 on the leaderboard right now.
Mm.
Josie and I both use custom keybind sets. Nenri uses defaults, and I don't know how. Their hands are so fast. So yeah, custom keybind sets. I have piece filters. So these are just basically in the order that I solve pieces. And I basically use ZZ without edge orientation.
Oh, you do use
So you'll
ZZ.
notice I solve the middle. And the reason is inserting F2L pairs. In 3D, inserting an F2L pair is 3 moves.
Right.
In 4D, there's 2 kinds of F2L pairs. So if I solve to here, there's, let's see, I'll do this. There we go. So there's 2 kinds of F2L pairs here. There's this, which we call F2LA. That's equivalent to your 3D F2L pairs. There's an edge and we call it a ridge and an edge, but it feels like a 3D F2L pair. You can insert this in 3 moves.
Okay.
This is called an F2LB pair. Says A and B.
Mm-hmm.
This is an actual edge and a corner, but it takes 5 moves to insert it.
Can you demonstrate?
And that's yes. So if I let's see, inserted. So if I were just doing, let's rewind a bit. Actually, so if I'm here, this I can insert in 1, 2, 3 moves. If I have this pair, yeah, sorry. Sorry. So here.
What is
This
the
is-
top here? Like, is it which is
Yeah. So my last layer is inside purple.
the? Okay.
I can do this, and now my last layer is on top, and this looks like 3, doesn't it?
Yeah. That makes...
Some people solve this way. I find that very difficult because I can't see as much.
Yeah, I'd imagine you want to
So-
pay attention most to the thing in the center. So.
Exactly. Yeah. So we can solve this in 1, 2, 3 moves from it being on the top. But this pair needs 1, 2, 3, 4, 5. So 4, 5 there is 1 move if I click on the corner, but using keybinds it's 2. 6, and then 7, which again that's 1 move if I click on the corner in the right way.
Yeah.
But in practice, it's 7 keys.
Okay, so
to do this.
you're putting in F2LA pairs, and then within them you're putting in F2LB pairs. Like in
So
between
the A
them.
pair is just these 2 pieces.
Right. So I'd imagine you're
the
gonna
B-
you're gonna make the bottom. Is it still like CFOP effectively? Like, are we still doing like the bottom?
Yeah, we're
piece
still doing
cross
cross
first?
F2L, OLL,
Okay.
PLL.
So it's just
each of those steps.
F2L1,
yeah.
F2L2, OLL, PLL kind of.
You can do it that way. F2LA and F2LB. You can do
F2LA,
like that.
Yeah.
The reason that I do it slightly differently. So for my cross, I'm gonna just solve these 4 pieces. This is equivalent to EO line, basically, or line, I suppose. EO line is edge orientation and basically the down front and down back cross edges.
Mm-hmm. Down.
So I'm about to solve. Yeah.
Down front and down back. Okay.
So I'm going to solve this in 4D and then I'll show the equivalent in 3D.
Okay.
So if I go here and open a 3D Rubik's Cube, full, I have just done this, and I will, this is what I've just solved.
Yep.
Basically.
Yeah.
But in 4D.
That is. Oh, that's what that is. Okay. Yeah. That makes sense.
Yeah. Let me hide this.
You called that the EO line?
So this is a line in 3D. If you do edge orientation at the same time as solving that, it's called an EO line in 3D. In 4D, we call this mid.
So like edge orientation in the ZZ sense.
Yes, but we don't orient edges in 4D. It's not worth it.
Okay.
You can, but yeah, I don't think it's worth it. So in here in 4D, it's just called mid. Let me go here. There we go. So we've done the middle section, and now we do left. This is mid, and then we do left block and right block. So in 3D, left block is whoops, should be here. Yeah. Yeah, this makes sense. So in 3D, left block would be these pieces.
Mm-hmm.
It'd be cross and two F12 pairs.
Yeah.
There.
Mm-hmm.
In 4D, we have one cross piece. There's an F2LA pair I just inserted.
Okay.
And here's an F2LB pair. And you'll notice as I'm doing that, I'm taking full advantage of this free face. Like in 3D, in this case, you'd have to hide the corner, bring the edge around, and pair it, right? This is equivalent to like if I had this case in 3D.
Uh-huh.
So yeah, they're opposite. I have to hide the corner, bring the edge around, pair.
And
In
what's-
4D, I could just put it directly there using this free face.
Oh, using the R. This is effectively the R face that is.
Yeah.
I see.
And so that's why I solve like one side and then the others, because I can
Right.
use that extra side.
As opposed to just
Like
C4.
here,
Yeah.
yeah. Could do 1, 2, 3, 4, 5.
Right.
Or I could do 1, 2, 3, 4.
Right.
And now I've solved these 3 A pairs.
Mm-hmm.
I could solve the next A pair, but then I would end up with some pieces stuck in the front sometimes. So by solving the next B pairs next, I can make it less likely that I'll have stuck pieces inside pairs.
So like kind of block building is.
Yeah, it's very much block building.
Okay.
Yeah. A lot of our 4D techniques, like block building, is actually extremely valuable in 4D. Not so much for speed solving, but it's the only technique that scales well in higher dimensions. F2L gets worse and worse. Block building remains good,
Gotcha.
basically. And now I'm solving the right side. I got the section. So I finished left block. Now I'm on right block.
You said it scales with dimensions.
Yeah.
Implying that there are 5-dimensional cubes that people do.
Oh yeah, people have solved
my
up to
God.
7 dimensions.
My brain is
I
about
can
to get
open
blown
in this
away.
program
Holy crap.
3 to the 5.
Oh.
Not this
God.
program. I can open in this program
3
to the 5 and the D here. Yeah.
Holy crap.
We can do 3 to the 5. No, we can't. Because I broke it. Hold on.
Changed. Yeah.
Yeah, yeah. There we go. There we go. Here's a 5D cube. Let's do 4D
Oh
rotation
my God.
and 5D rotation.
Wow. So this has
We can. Yep.
10 faces, or sorry, 10.
Yep. 10 facets, we call them.
Facets.
This is why we use the term facet,
10
because facet
facets.
generalizes in the way we want.
Right. 10
I can
facets.
do 60, which will take a minute. This is going to be only 2 to the 6.
What is the highest dimensional puzzle someone has solved by hand?
7 dimension.
Wow.
So here's 60. It starts to get a little difficult to keep them all on screen, but that's why we can space it out. Space it out. There we go. And for 7D, I don't know if 7D works. Let's try it. I'm going to run it as a release build, though. Because it's going to take a while otherwise. So while that builds, so that I can demo 7D, I'm going to finish this solve. And then explain how last layer works. Let's see.
So it's still the same principle of like compose the pair on the top layer and
Yes.
then insert.
Yes. So
Okay.
I can form the pair here and then insert it. In this case, I'm actually doing same thing we do in 3D sometimes, where if we have, let's see, if you have a pair that's like this,
Yep.
you could
You
pair
can-
it
Yeah, pair.
and then insert it,
Right.
Um,
But it's just
or
pair
you can
during
just
insertion.
pair it as you insert it.
Yeah.
Yeah, you can just pair it and insert. And so I can do the same thing here. Exactly the same case.
Gotcha.
Of course, it takes more moves because this is a V pair,
V pair.
F2LB.
Oh, B. Oh.
Yeah, it's F2LB is with the corner and edge as
Yep.
opposed to an edge and ridge.
Yep.
So now last layer. So I have to orient this. So my goal is to get all of the purple stickers on the I cell here on the
Mhm.
inside. So I'm going to start with edges. So I'm basically going to do 3 look. Ridges. These are ridges, but they behave like edges. So So I'm gonna put this here, and then now I can use big moves and treat it like 3D.
So-
So I just did FSXE F prime.
The terms are.
Yeah,
The
pieces.
terms are edges, ridges, corners, and what?
Yep. So we have ridge has 2 colors,
Mm-hmm.
edge has 3 colors, corner has 4 colors.
And that's all.
And I can explain why.
Is there like what's the equivalent of
Yes.
the center?
The centers are centers. Sorry.
Centers. Okay.
Yeah. So, and the reason we do this, we're following these terms. Here.
Gotcha.
So vertex is corner, edge is edge, face is face. But in 4D, faces and ridges coincide.
Mm.
And then facet, which we call center, and then the polytope itself.
Okay.
So if you replace facet with center and vertex with corner, then everything makes sense.
Okay. Yep.
Yeah. And we kind of try to draw from like walking along like opposites here. Like we'll prefer ridge over face and prefer edge over peak because that gets us the behavior we want. It matters more to us. Like we don't care that a center is a cell because it behaves like a facet. No matter what dimension you're in, they kind of behave the same.
Okay.
So we try to call the cells facets instead.
I see.
Okay, this loaded. So let's try 2 to the 7. See if that loads. And I want to optimize this a lot more.
How many
it
like
already got
polygons is it going to be like rendering here?
Well, it's yeah, it's bad. Because it has to make because it has to make a polygon for every single polygon in the shape.
Yeah.
Right. Think about how many like vertices you have in a hypercube,
Yeah, it's a lot.
or how many edges you have in a hypercube. Yeah.
It's exponential, right?
Oh.
This is exponential.
Oh yeah. With number of dimensions, yes.
Yeah.
The number of pieces is exponential. The number of elements in each piece is exponential. It's bad. So we'll let that load for a while.
Wait, so
yeah.
sorry, you were saying something about FSXE F prime.
Yeah.
Is it are the
Yes.
Are you gonna tell me that the OLL logs are the same or something?
Yeah. Almost
Wow.
every single algorithm I use in 4D is modified from 3D. So F, R, U, R prime, U prime, R prime.
Wow.
Now here, I can manipulate these edges just like corners. So these 3 form a soon. I'll just do a soon.
Huh.
And now those are solved. And let's rotate over here. Those 3 form a soon. Let's highlight these. So, or anti-soon. So I'll do an anti-soon. Nice, those are solved.
Wow.
And now, these aren't a valid OLL case, but I can rearrange these pieces, and now they are. And so what I'm doing there is a technique called HactarCE, which is using this right face to manipulate this purple cell as though it's a 3D Rubik's Cube. So I can do, on this inner cube, I can do an R2,
Right.
U, R, and because I did 4 moves total, this right side went back to solved.
Yeah.
But the purple was affected.
I see.
Whatever here.
So you turn the purple thing
So,
and just do 4 turns on the right face, and then.
Yeah, exactly.
Okay.
Yep. And so now I've solved the centers and the center was already solved. Center is that one. I've solved the ridges and the edges, and now I just have to solve the corners.
Okay.
And for that, I can use HactarCE. But instead of HactarCE on purple, I do HactarCE on white. So right, if I treat this guy as a 3D Rubik's Cube, these are its stickers. And if I do an OLL algorithm, like say the H case, I can take these 4 stickers and put them on the top here.
Right.
If I do it right, which I did not. What happened?
You did the thing twice.
Okay, yeah.
You were already in the correct place.
Yeah. Okay, there we go. Thank you. So yeah, now I got those solved. Now, one of them was wrong, but that's okay. Still worth it.
Cool.
Yes. Now, when I'm doing this, I'm not actually doing HactarCE. If I were to actually do HactarCE, it looks like this. Very slow. I don't like doing that. So instead, we do a thing called HactarCE cancels, which I will explain after the solve because I need to have a solved puzzle to demonstrate it.
Just as an FYI, I have to go in like 15 minutes.
Yes.
So.
Okay, yeah, I'll be done in 15 minutes.
Okay.
We'll be done with this solve very, very soon. So now we've oriented them all. Now I need to move the centers around. So if I do this, yeah. So I can use a U-perm to move these around because these behave like edges. They're ridges, but they behave like edges. If I put it here, then now that's a 3 cycle. So I'll just do another U-perm. And now this is just a 3D Rubik's Cube. I know how to solve that.
The remaining pieces are a 3D cube?
Yep. Yep, there's the 3D Rubik's Cube.
Oh, wow.
And I have to solve it using RKT, but that's not so bad.
Right.
It's bad in higher dimensions.
Is this the
And I use
equivalent of
the
like an AUF on a...
Yes. No, this is PLL. This is the equivalent of PLL.
Oh.
Um,
Okay. I guess I can see that, yeah.
yeah,
The equivalent of AUF is just rotating the 3D cube that remains.
exactly. So now I have AUF.
Okay.
There we go.
Huh.
So, so the thing that I do instead of RKT is, so let's say I'm doing RU R prime U prime,
Mm-hmm.
right? I could do it like this: RU R prime U prime. Or let me do it without the flashing. Sorry, RU R prime U prime. So that works, and I've manipulated only the purple. Everything else is solved.
Mm-hmm.
There's another thing I can do. I can actually do as many moves as I want here, as long as I later undo them. And I've just done things on purple, but I didn't need to rotate purple as many times. In fact, if I am very careful and flip purple around this edge, and then undo my moves, and then flip purple back, you'll see I did RU R prime U prime on purple, but I only had to rotate purple once.
You did RU...
So I did
you're
argue.
saying the pieces, or
Yeah.
the edges and corners within that purple cube, like...
Yeah,
permeated with
they
each
had an
other?
RU R prime U prime done to them,
Gotcha. Okay.
but I didn't affect the rest of the puzzle.
Yeah.
And I can explain why this works. So if I write out RU R prime U prime, so what I'm doing using purple, using orange and yellow is RU, so RU, and then U prime R prime. Okay.
Yep.
If you look at what happens to purple, it gets the RU happen, and then I swap
Then
R and U,
Yeah.
right? And so
Yes.
if I swap R and U, well, this becomes R, that becomes U.
Right. But you are scrambling the rest of the cube, though. In the process.
And then I unscramble it.
Right, but I'm saying like the PLL got manipulated.
Yeah. The important thing is that this is all I'm manipulating is just purple, as opposed to the rest of the puzzle. So this is a way that we can do
purple,
RKT.
You mean the purple, the layer that contains
purple,
the purple
the purple
things.
pieces, right? Because this is a purple piece.
Right. I'm
It's like me saying
thinking of
that
like
a T-perm
stickers
only scrambles yellow.
as independent objects. Or
Yes,
something.
this is like me saying I only scrambled yellow.
Right. Yeah.
Because it's yellow pieces.
I'm with you.
Yeah. Cool. So, and we were a search program for this to find these ways of flipping things around
Mm-hmm.
to manipulate pieces, to manipulate like just purple, basically.
Yeah.
And do common 3D algorithms. So a whole bunch of them have cancels. There's a really nice one for Soon that only has 2 flips in it. So instead of flipping purple, I instead can flip everything else. Whoops. I need tools, puzzle controls. I instead can flip. I can't. Yeah, hold on. I can't demonstrate it easily. Or there. Yeah, instead of flipping purple, I can flip everything else. And that way it feels like I'm doing a 3D algorithm. Because my inputs are RU, flip, R prime, U prime, flip.
Mm-hmm.
Where the flip is the funny thing. And now I'm manipulating purple. But it feels similar. It's like I'm doing a 3D algorithm. I just added a couple extra key presses in the middle.
Right.
So the muscle memory overlaps nicely.
I see it. Cool.
And so we have one that's nice for Soon. And I use that one. There's another one for double Soon. Double anti-Soon. We have one for U-perm. Actually, quite a few for U-perm. There. I use a funny U-perm algorithm that works well ergonomically for this. And we have one for A-perm. Hold on. Oh, jeez. There it is. And again, that's
Yeah.
like it's from a funny angle, but
Right.
it's very ergonomic.
Cool.
Yeah. Let me do one at full speed.
Sweet.
I should eventually do a talk on circle puzzles and block building if people are interested.
Yes.
What is a circle puzzle?
Ah, we'll get to that.
Okay.
It's
Yeah, I'm interested.
have you seen the mathematics of geranium puzzles? That video.
Oh, I haven't seen the video, but I'm aware of what the geranium puzzles are. Like the 2D
Yeah.
ones where you like
Yes.
twist the circle.
Yep,
And...
those are circle puzzles.
Okay.
In general, geranium's a specific family of them, manufacturer of them, something like that.
Is that very puzzle? I think that's very puzzle. Who makes those?
Yeah, very puzzle makes a lot of things. So circle puzzle is the term we use for that sort of thing, where you have
Gotcha.
twisting circles.
Yep.
And geranium is a special, quite cursed case in the sense that it is jumbling and very heavily bandaged
I see.
and quite
Yeah.
bad.
Yeah.
But there are nicer ones.
Yeah, absolutely. I'd love to hear about it.
I want that talk too, because if you can formalize that, like I understand it, some of it intuitively, but it's like block building on circle puzzles formally. I don't really. That's fun.
I mean, I don't really understand it that much.
Well, then
either.
you'll have to do that before you want to give a talk on it.
Right.
The problem is no one understands it fully yet. Like we're still developing the theory of that.
Mhm.
No. There we go.
I've been able to follow this solve. I'm so happy. Like I can tell what
Yeah.
you're doing.
Yeah, you could watch world record. If you could follow this, you could watch world record videos and understand what's happening. Because this is not much slower than that. A little bit slower. There's some details I have left out in case you ever attempt this on your. Oh, that was good. Okay.
That's awesome.
Some details I've left out in case you attempt this on your own. You'll have some exciting things to find, even if you try to apply the algorithm or the method that I've described.
I kind of want to just try it naively because like when I
Yeah,
thought about doing this,
that's good
I
too.
was planning on just like showing up, trying to identify commutators, and just like going like piece by
Excellent
piece
idea.
and doing that. So
Yeah.
now that I know all the cheat codes, I'll probably still try the way that I was going to try to do it, but this is cool.
RKT is the only cheat code that I've given you. This general outline of a method is going to make your life faster, but not easier.
Right. Yeah, that makes sense. I imagine the hard part is like because I know enough puzzle theory that I think the hard part for me will just be wrapping my head around the geometry of this thing in the first place.
Yes.
So
Yes, which is perfect.
yeah,
That's good. Oops.
So Hector, since
Yeah.
2Swap has to go, do you have anything else for the recording?
Feel free to
I
continue
think so.
and or
Okay.
record for yourself.
Okay.
And I could concatenate videos if you want to, if you like really want to continue. I just have to drop off, so I'm gonna cut my recording here.
Okay. I don't. There's not much else unless you have more questions.
I still have a million minus one questions.
Okay,
They
great.
don't need to be in the recording.
To stop the recording, but I can
I'll stop after the
start
solve.
my own. Okay. And then I'll start my own recording, and then if it's sufficiently interesting, I'll send it to you and you can concatenate them.
Okay.
Yeah. Thank you so much.
Thank you. This is fun to watch.
Yeah. Oh no. Okay. Yeah. So as I'm doing this, I'm actually paying attention to the grayed out pieces to make sure that my those things are solved,
Mm-hmm.
or close enough to solved. Oops. Nope. There we go. So that would be a +2 seconds because I turned it after the timer stopped. Okay, excellent. That's the end.
Cool.
Let
Thank
me
you.
open OBS.
Thank you.
Yeah, thank you. See ya.
Sweet. I'm gonna cut the recording.
Let's see.
All right. Bye bye.
Okay. And I'm recording
And
again
bye bye
now.
from me now.
All right. Yeah, so the audio will probably change. Okay, so Axiomatic, you had more questions. Go ahead.
I had more questions. I don't know if Axiomatic does.
Oh, I'm sorry, Mattspin. Mattspin, you had more questions. I mixed it up.
Yeah,
Yes.
so just for context here, I am not like the cubist, whatever.
Yeah.
I solved a basic Rubik's Cube by following instructions
Mhm.
and did it a few more times, and that's about it.
Yeah.
But I have played with, I assume you're familiar with a very old program called Magic Cube 4D.
Yes! I solved on
And
that
I'm wondering,
at
like,
first. This is
how much,
yeah.
how much of that is in this, or have you communicated with like the people who made that?
Oh yeah.
Or...
Yeah, the people who made that are Don Hatch and Melinda Green, if I remember right. Might have been someone else involved. I don't remember.
No, that's it.
And maybe Royce Nelson. I think Royce Nelson just made Magic Tile. But yeah, all of those people are in the same circles and stuff. I am basically trying to kill Magic Cube 4D because I don't like it. Now,
Okay.
I think it's great software. It's just missing nice features that we want, like piece filters and keybinds.
Yeah, I mean,
but-
I was probably using it like 25 years ago or something, and this didn't exist then.
Right, exactly. And also I wanted GPU accelerated. Magic Cube 4D uses CPU rendering, so the outlines are laggy, even on a decent machine. And it can't do anti-aliasing, things like that. So yeah, I'm trying to, and Magic Cube 4D can do other shapes though, which is why I'm Hyperspeed Cube 2, I want to support those. So yes, Magic Tile is very much the inspiration, Magic Cube 4D is very much the inspiration for Hyperspeed Cube 2. It's basically just trying to rewrite that in Rust.
Okay.
And to run on the web. Hyperspeed Cube 1 runs on the web. And Hyperspeed Cube 2 hopefully will as well, although it's going to be a while.
Okay, nice.
Yeah. What else do you have?
Before I keep going, I just want to make sure that Fractal or Axiomatic System, you also have a chance to ask questions.
Fractal works here, so...
Okay.
Yeah, Fractal's in voice chat with me every day as I'm developing Hyperspeed Cube, so they know all this stuff.
Yeah, I don't know enough about 4D geometry to ask intelligent questions. I'm just here for the ride.
That's so fair, yeah.
Okay. Well, I think I only have. Just a couple more.
Okay.
So before, when you were talking about the jumbling stuff,
Yeah.
you got into a side comment about if you were to build the 3 to the 4
Yes.
in 4D,
Yeah.
then you could rotate it all these ways.
Yeah.
So, just to make that a little more precise, a Rubik's Cube, a physical Rubik's Cube,
Right.
you take it apart and there's those springs that connect the center of the face pieces.
Yeah.
And then there's I know how a physical Rubik's Cube is made.
Yeah.
And so are you saying that people tried imagining how that would be done in 4D and failed? Or there hasn't been much effort to imagine what the physical things in 4D would be?
What I'm saying is that from our guess is that if you tried to build a 4D Rubik's Cube in 4D, the way that we build 3D Rubik's Cubes in 3D, then what you would end up with is a puzzle that works like this, but can also have these 9 pieces move independently. So
Okay.
that is our guess, based on our intuition about these geometries and mechanisms. And the fact that those pieces can move. There's nothing blocking those pieces from moving. And it seems strange to say that they can move, but only when attached to one face or the other. Because mechanically, like even if you treat them as just hypercubes existing in a space, they can move on their own.
Okay.
Yeah.
Yeah, I haven't done a lot of 4D engineering, so I don't know
Yeah.
if there's
The same way that like if you have it's exactly analogous to circle puzzles actually. Like the way that those can move at all is kind of like I don't know exactly how to describe it, but I'll just say that we're pretty confident this is how it would work if you built the thing in a rigid body environment, like simulated or whatever. Yeah.
And then the last things I was wondering are about possible future features.
Yes.
So I don't know if you want to get into that.
Oh yeah. So mostly it's quality of life stuff. I want it to be easier to write these puzzle definitions. I already have the piece filters nicely, but this program needs keybinds. I also want to extend it to support magic tile puzzles. So not this page, but this page. So this is a program that simulates puzzles in spherical and hyperbolic geometry, 2D. So here are some hyperbolic ones. This is a normal Rubik's Cube, but with a funny spherical projection. So I want to support these. There's also discrete right here. So this is the 2D conformal boundary of 3D hyperbolic space. So if you have a 3D hyperbolic tiling where all of the cells are hyperideal, meaning they are infinite and like extend past the boundary of the hyperbolic space, then visualize the boundary of the 3D space is going to be like a 2D sphere, basically. And that's what we're viewing here, is that 2D sphere. And each of these colored regions is one of the cells that escapes the boundary. And you could build puzzles in this space. No one's done it before, although this program can sort of support it, but it's barely usable as a puzzle simulator. Remember there our mirror construction. If you try to remember we had the number of mirrors was corresponding to the dimension of the space. This has 4 mirrors. They're the red line, the green line, the blue line, and the yellow line, which is more than you would expect for 2-dimensional space. So this is a very weird kind of geometry where you can get more mirrors squeezed in there and get puzzles that are 4-dimensional sort of, but visualized on a 2D plane. So I really want this in the program eventually, but that's a little ways out. What else? I want interactive features, so interactive puzzle.
What exactly am I looking at?
Yeah. So I was trying
in that other image. What?
Yeah. So this is really gnarly. So are you familiar with 2D hyperbolic tilings?
I'm familiar with the disk projection. Is it a collection of those filling in another disk, or is it more involved than that?
These are visible in here, but this is more involved. The way we actually generate this is by starting with a 3D hyperbolic tiling. So let's say you have a bunch of dodecahedra and you put 4 of them maybe around each edge. So if you put 3 dodecahedra around each edge, that turns into a 120 cell if you fill in all the dodecahedra. If you try to squeeze 4 of them around each edge, same way if you try to fit 4 pentagons around each vertex, you get a hyperbolic tiling. If you fit 3D shapes and there's too many of them, you get 3D hyperbolic space. Hyperbolic honeycomb.
Right.
And so there's a lot of uniform honeycombs in hyperbolic space. And the cells are finite. Like this one, the cells are dodecahedra. Dodecahedra are finite. It's reasonable. Some of these, if you start with a hyperbolic tiling in 2D and then you put 3 of those around each edge, your cells are themselves hyperbolic tilings. And those are going to be infinite, like hella infinite. In fact, they're not even like each cell is infinite, as well as the tiling being infinite. And so if you think about like just looking at the sky, if you're in one of those tilings and you look outside and you look infinitely far away, and you color each point in your field of view based on what cell is there, if you walk in that direction infinitely, you get the boundary of the space. That boundary is what we are visualizing here. Because that boundary is two-dimensional. The boundary of a 3D space is 2D. And we can build puzzles in that boundary. Does that make sense? Let's see, visualizing hyperbolic honeycombs. This is the research that this work is based on.
Think?
Yeah, so this did not make sense to me the first several times that I learned about it. Luna Heron had to explain it to me many times. So this is work by Royce Nelson and Henry Sagerman. They did one of them, I think it was Royce, did a talk on it. Which is not...
Okay, I think I get it now. But don't ask me to explain it back to you.
Yeah, that's fair. Let's see, hyperbolic honeycombs, conformal boundary. There is a talk about this somewhere.
So Henry Segerman has a Bridges 2018
That's
talk
the one.
on visualizing.
Yeah, this is it. Segerman did this. Yes. So here's the talk where I recommend watching this, possibly multiple times. But that explains what we're doing here. The new thing we've done, they had a renderer for this on the CPU, which has a lot of really, really cool features. If you look in their paper, there's some gorgeous images. The novel thing here that Luna Heron and I did is make it run on the GPU. So this is real time. We can interact with this. In fact, let me see if I can get this working. I don't know how to operate the program very well, even though I understand the algorithms going on. Let's see, PDF. Here we go, yeah. Yeah, there's some really, really nice images, which are, yeah, so here's, let's see, here we go. So here's an example of a hyperideal cube, where it's extending and you see it like intersects the boundary here, boundary of the whole space. Okay, here I have it working.
Yes, like the Poincare disk, that's the Poincare sphere.
Yes,
that the central
exactly.
cube
Yeah.
is intersecting.
Yeah. Oh, this doesn't have the, does it have the recentering? Hold on. I think there's an update. Nope, there's no update, darn. Could have sworn. Automatically move camera reference, bingo. So now if I go, yeah, this is better. So we have a fundamental region here, which is the gray triangle, which is moving around to keep it numerically stable. So this fundamental region, the gray triangle, is getting copied around, reflected across all four mirrors. But that's not super important right now. Let's see. The important thing is color by quotient. There we go. Is that what I want? Color by neighbors? I don't actually know how to. Color scale? There we go. There, now I'm recreating that image. Yeah, so I can just play with this interactively, which is so cool. And if I click, ignore the line coming out of the... Here, let's turn off draw path. I can actually twist this. This is a puzzle. This puzzle has, I think, only two piece types. Centers and effectively edges, or ridges. But yeah. So anyway, I want to integrate this into Hyperspeed Cube 2, but this is spooky. Yeah. Very cool, though.
Yeah, I saw how far your twists were propagating, and I just thought, oh no.
Yeah. I don't think this program has scrambling in it. 653. I can also show 633 And reset camera. No, I can't show 633. 4, 3. There we go.
Is
There's
doesn't have a boundary.
yeah, but there's a way to do. Oh, part of the problem is also these things, the relations.
Yeah, but that doesn't.
There's a way to get it to show a hexagonal
You
tiling.
show
That's I don't remember what it is, but there's a way to make it just
hexagonal tiling. Just 6-3. You mean?
Yeah, maybe I just do 6-3.
Remove all the
6-3-2.
relations.
Yeah, 6-3-2 with no questions. Generate? No. There's a way to do
0-1. Remove all of the lines.
Oh, thank
you.
Yeah, there we go. Okay.
Then type in 0-1, 1, and then semicolon 1.
This?
That might.
Oh, maybe? This looks spherical. That should not be spherical. I don't know how to use this program.
I don't think 632 is valid because what are you trying to construct? It's 2 hexagonal tilings.
I was trying to, I'm trying to do. No, that's what it. I've definitely seen a hexagonal tiling in this program before. 5-3 maybe?
Try like 6-3-8, right? Something that's.
Oh, there we go. There's a
definitely-
dodecahedron. That's what I want. So
Right,
6-3. There we go. There's a hex tiling. That's what I was looking for. So yeah. Yeah, and this path it's drawing is the path to get from this point back to the fundamental region by hopping over the green mirror and then the blue mirror and then the green mirror and then the red mirror and then blue and then red, green, red. Yeah. So anyway, yeah, this is also a thing I want to integrate into Hyperspeed Cube too, eventually. What else? I have a whole list of things.
Circles are happening soon.
Circle guy, yep. So I want the circle puzzles in here. I basically want this to just be the puzzle program that has everything. With the idea being that if you write a puzzle backend for Hyperspeed Cube, all you need to do is write the simulation and the rendering. And then you get, basically for free, you get piece filters, you get color palettes, customization, you get all this user interface stuff, you get log files, you get automatic integration with the leaderboards, all that stuff for free. And so we can have one unified thing. And it's very modular. You can take individual pieces of Hyperspeed Cube and use them for other puzzle programs. For example, there's a program called Circle Guy, which, as of last week, now uses the same programming language that Hyperspeed Cube uses, the Hyperpuzzle script. So Circle Guy is able to use this programming language because it's really nice for defining puzzles. Yeah.
Cool. So yeah, can I ask if
Yeah.
a couple things are on your roadmap or
Go for it.
your wish list?
Yes.
So one thing that kind of stands out to me, and I know as a financer, has there been any talk about features for colorblind people?
Great question. Fantastic question. So I have color customization. You can customize the global color palette. So you can change these, and these will take effect across all puzzles too. Features like patterning on the stickers is something that I would like to add. Unfortunately, there's not a lot of people in the existing hypercubing community who are asking for that, so it doesn't end up being on my radar very much. But that's a really good point. So yes, that is something I would like, because that's relatively easy to do, to just have a shader that instead of putting the color does some fine-grained pattern on it. If you are or know someone who's colorblind who would be able to give feedback on that, then that would be good. So that, because I don't want to develop a feature unless I know someone who will can tell me if I'm doing a good job with it.
Yeah, I mean, so for the most common sorts of colorblind, there are palettes already up to
Yes.
some relatively small number of colors.
Yeah.
But it looks like this has a couple challenges. One, you often need more than a small number of colors.
Yes. Yeah.
And two, for maximum compatibility and the few people with total color blindness, like you would want
patterns.
like you said, some sort of like textures or like different kinds of shape dot patterns or something, and that is like that you would really need user testing for, like you alluded to.
Yeah. So one of the by the way, our 7D puzzle loaded. There's another couple things we can do. For the 120 cell, one thing that we've talked about is having a feature of dynamic recoloring. So like no one, even with like typical vision, is going to be able to distinguish 120 colors nicely. But we could have it integrated with piece filters so that whatever faces you're displaying have distinct colors assigned. And we just, as you solve different pieces, different parts of the puzzle, we can change the color assignments to just have unique colors for the section you're working on. I don't think that helps much for Hypercube, because you still need like a good set of like 10 or so distinct colors. But it's something. So that's something we would like to have. Why is this erroring? So that's something we'd like to have, is dynamic recoloring. But I think textures is really the nice solution to this.
And the last thing I was thinking about, you're talking about crazy hyperbolic stuff and spherical stuff, and Hyperspeed Cube has higher dimensions.
Yes.
So I don't know, has there been talk about the other 3D geometries or higher dimensional geometries?
So 3D hyperbolic is something that we want to do, but probably won't be able. Cutting shapes in high dimensions is very difficult if those shapes are not like straight line polytopes. The original version of Hyperspeed Cube 2, I was trying to implement a cutting algorithm that would have worked in hyperbolic geometry and fell flat on my face. It turns out it's really hard to do cuts with curved surfaces. And you basically need that for hyperbolic stuff. So the good news is this program actually can simulate puzzles that are equivalent to hyperbolic 3D puzzles. Because remember, this is based on a 3D hyperbolic space. As long as your cells are all hyper-ideal, you can simulate the puzzle. And even if you have a hyperbolic tiling that is not hyper-ideal, you can take a hyper-ideal one and quotient it to get a non-hyper-ideal, to get one that's equivalent to a non-hyper-ideal one. So if I close this program and restart it, because I don't remember the original, this tiling might already be quotiented, actually. Let's see. Bring the color scale down. Yeah, this is already quotiented, actually. You can see that these two faces are the same. Yeah, these two faces are the same. So these are actually, this face here is a triangle, not a hexagon. So this tiling is actually 353, which is, I don't know, but it's something. Yeah, so hyperbolic 3D we can do using this. Anything bigger, cutting it is going to be very difficult.
3 is like a pentagonal tiling, right?
Pentagonal tiling? What?
Because it's like 5 triangles.
Oh yeah, yeah. If I change the, I think if I make this like 0, 2.
Because it's like 3, 5 on the 3D and then 5, 3 on the other one.
Yeah. Oh yeah, yeah.
Because 3, 5 is just a pentagon.
Yes. No. 5 is a pentagon. 3, 5 is icosahedron.
Oh, sorry. Yeah.
Yeah. So there is one program, MHT633, right here, Magic Hyperbolic Tile 633. This is proper 3D space. 6-3 is a hexagonal tiling. 633 means you took 3 hexagonal tilings around each vertex. And this program simulates it. It just simulates this one puzzle. I want to have this in HSC2, I don't know how this program does it. I'm terrified of it. And I don't think I could do it in general for hyperbolic tilings. We might be able to just manually code this one. So to answer your question, yes, it's hard, but I want it.
So then, because hyperbolic is not the only 3D geometry. Have you tried reaching out to Xenorogue?
Oh God,
Did you know?
I'm too scared.
Yeah, it's like that seems like the natural thing. Like, if anyone would know how to do this,
right,
like that would be the person who would know how to do this.
A lot of the more exotic things like nil, I don't know how to do puzzles in it. Like we've talked a little bit about that, and our consensus has generally been like we're not sure that the space has enough symmetry for twisty puzzles. But I don't know. Yeah, maybe. If possible, I would love to do that.
Okay, yeah. I'm just like, I don't know what your
we're
workflow and pipeline is.
Yeah, we spent the last like couple of years developing mathematical frameworks for what is a twisty puzzle, what things do you need in order to construct one, and we might have enough tools now that we could actually look at something like nil and say, can we get those twisty puzzle axioms to happen in nil? I don't know what the answer is to whether that's possible.
Fair enough.
That's a very good question, though. The colorblindness thing is a good point. I'm going to write that down right now before I forget it. Not as a thing that will happen soon, probably, because there's a lot that I need to do in Hyperspeed Cube soon. Before, like right now, people can't even do solves in Hyperspeed Cube 2. It's not set up for that. It doesn't have those features. I've been so busy building the infrastructure and making sure everything is like stable and like, because the log files, I don't want people doing solves until the log file format is stable. And I can't know that the log file format is stable until I've implemented enough features that I know what they need from the log files. And I don't want to make a bunch of puzzle definitions until I know that I'm writing those in a way that's good. And I don't want to have to rewrite a bunch of puzzle definitions too many times.
Makes sense.
So, yeah. But yes, I do want to have accessibility features. Yeah. Any other questions?
I'm all good. Thanks for the presentation.
Okay. Yeah, thank you so much. This is fun.
Yeah, no, this is interesting. I'll have to
give it a try.
See about getting into 2D
hypercubing,
puzzles and work my way up.
Yep. If you go to Hypercubing XYZ, Introduction to Hypercubing is at least the first video I recommend. The first video is basically just what I've already told you, but only the parts about starting 3 to the 4. But this also tells you how to use piece filters and keybinds if you want to do that for your first solve. But for getting started, I recommend just like try to solve it, see how far you get. If you have enough understanding of 3D that you could solve it without a tutorial, basically, like developing your own algorithms and stuff, then you probably can do 4D.
TwoSwap gave a talk that kind of helped everyone do that.
Oh, excellent. Yeah. So, yeah, you probably could solve the 3 to the 4 then.
We should probably link to that talk somewhere on the wiki.
Oh, yeah.
Because that's the one thing we don't have, right?
The general puzzle solving thing? Yeah.
Yeah.
Yes. I don't know if I want to link people to an hour and a half long talk if it's long. For purposes of hypercubing learning resources.
Yeah, no, it's 2.5 hours.
Yeah, 2.5 hours. Yeah. Yeah. Okay. Cool.
2.5 hours and undirected, so not the best place to funnel people who want to learn.
Right. Yeah. Okay. I'm gonna stop the recording now.